Okay, so the next measure of fit is the root mean squared error. And it's very similar to the standard error of the regression, except that we do not correct for degrees of freedom. In other words, the root mean squared error is equal to the square root of the sum from I equal 1 to n of the error term hat squared over n. So we're not correcting for degrees of freedom. In the previous case, we had SER, we're correcting for degrees of freedom if I have one X or two regressors, and we're correcting for degrees of freedom if I have multi-regression. So it's either n minus 2 or n minus k minus 1. In the root mean squared error, we do not correct, we just divide by n. And it's like very similar except for this part. And I want you to notice that if I have a large sample or if n is large, okay, both are almost the same. So SER and root mean squared error will give very close results. Okay, so they will give very close results. If you're talking about a sample size that is equal to 500, and if you're correcting for the degrees of freedom by saying it's n minus k minus 1, and I have, let's say, 3 x's and 1 intercept, then it's going to be 496. So if you divide something by 500 versus 496, right, it doesn't make a big difference. So if I have this one is 500 or 496, it will not make any a big difference in the results. Okay, and of course, if this 500 is 1000, then 1000 minus 4, of course, it's going to be like very small difference between the 1000 and correcting for degrees of freedom, which is basically 996. So if you divide by 996 versus 1000, it will not make a big difference. Okay, the measures of fit that we talked about so far are basically the R-square, the standard error of the regression, and the root mean squared error. There is another statistic which is called the adjusted R-square. The adjusted R-square is basically similar to the R-square, but it corrects for degrees of freedom. Okay, so it's very similar to the idea that SER corrects for degrees of freedom, but the root mean squared error does not correct for degrees of freedom. The R-square does not correct for degrees of freedom, but the adjusted R-square corrects for degrees of freedom. And a very important thing to note about R-square is that every time you're adding a regressor, every time you're adding an X, the R-square would keep on increasing. However, the adjusted R-square does not necessarily increase when you add an additional regressor. So why? Because if we notice that the way that this adjusted R-square is computed, so the adjusted R-square is, again, if you look at the R-square was 1 minus SSR over total sum squared. The adjustment of the degrees of freedom happens here, so it's n minus 1 divided by n minus k minus 1. How this happen? If you think about it this way, so 1 minus SSR, if I open up SSR, then it will have the y hat inside, so I have to divide by its own degrees of freedom. And if I divide by TSS, and if you open TSS, it's going to be like yi minus y bar, so I have just y bar to be estimated, so it's n minus 1. So basically, if you have it this way, then you can write it this way, and this is like the most common way of writing it. Okay, but it's originally this way. So the idea here, every time I'm adding a new regressor, what happened to the SSR? The SSR decreases each time you're adding a new regressor. However, each time you're adding a new regressor, the K increases, K, which is the number of X's. Okay, so I want you to think that adding an additional variable, like additional X, would have a positive effect and also can have a negative effect. What is the positive effect? Every time I add a new regressor, the sum of the squared residual is going to fall. Every time I'm adding a new regressor, the negative effect is that K, I'm sorry, as K increases, it basically decreases the R square. Okay, so I want you to think about it this way. If this one decreases, as I'm saying here, every time I'm adding a new regressor, the SSR decreases. If this one decreases, then I have a negative sign in front, then the adjusted R square will increase. And that's why we say it's a positive effect. Every time I'm adding a new regressor, the K is in the denominator. It has a negative sign before it, and there is a negative sign here. So every time I'm adding a K, the adjusted R square is going to fall. So we have basically two effects, and it's not the case that each time I'm adding a new regressor is going to have a positive impact on the R square, adjusted R square. No, it depends, because we have something that leads to a positive and something that leads to a negative effect. Okay, and again, it's very, very important to note that if I have a large sample size, or if n is large, okay, adjusted R square and adjusted R square basically will give very close results. Okay, because if you imagine, like you have here, the sample size is big, and I'm just subtracting these two numbers, so we would basically not make it as a big difference as if you subtracted -1 or you don't subtract anything. So that's why they would give very close results. Okay. Important notes to mention about high R square or adjusted R square. So high R square or high adjusted R square. It basically means that regressors explain variations in Y. But you can still have, right? You can still have many econometric problems. So I want you to understand that it's like it's not like the best thing to get a high R square, because you might still suffer from other econometrics problem. We might it might be the case that we have omitted variables problem. We might have insignificant coefficients. We might have biased estimators. Okay, we might have simultaneous causality. Okay, and so on. We can have like a long list, and everything is going to be discussed in the next topic. Okay, so the last measure of fit that I want to talk about is basically the Ftest. Ftest is used in order to do a test on more than one regressor. So if I have y, I is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus the error term ui. Okay, and let me put the i's everywhere. So it's a sample that goes from I equal 1 all the way to n. And suppose that you want to test two coefficients. So your null hypothesis is not only about beta 1, but it's about beta 1 and beta 2. So you want basically to see whether beta 1 is equal to 0 and beta 2 is equal to 0. And of course, the alternative is that beta 1 is not equal to 0, beta 2 is not equal to 0. So we call this restrictions. How many restrictions I have? I have two restrictions. And we call it by the letter Q. So Q here stands for how many parameters are tested under the null. So it's called a restricted model. So this is just the regular model, and this is what we call the restricted model. Restricted model, we're going to plug 0 for the parts that we're testing, so we're left with beta 3x3i plus ui, and we're going to call this one to the restricted model, and we call this one unrestricted model. And of course, when you run this model, you get, let's say, when you run this one, you get the yi hat. Let me call it 1, or instead of calling it 1, let me call it something that we remember. So let's call it let me call it u as unrestricted, and this one as yi hat restricted. Okay, and based on the idea of restricted and unrestricted, each time, let's say you like when you run this regression, you will get an estimated model, and this estimated model you will have an R-square that we call it unrestricted, and for this model you will get an R-square that we call it restricted. Okay, and based on the R-square restricted and unrestricted, we can compute the Ftest. So the Ftest is simply the R-square unrestricted minus the R-square restricted. Okay, and then you divide by how many restrictions I have, Q, over 1 minus R-square unrestricted, okay, unrestricted, divided by n minus k minus 1. And this has a distribution of an F distribution with Q and infinity. And then the distribution of the F is all, as you can see, square, so it's only positive side. And we will have also like the rejection region. Okay, so we have the rejection region, so we need to find like a critical value, and everything that is beyond the critical value is called the rejection region.